who's going to talk about, I don't know, I'd say like computer memory prototypes, sort of looking at circuit level on up, focusing on SRAM and RRAM. So just in the interest of time, I won't say anything else, but I'll just turn it over to you.
Okay, thank you, Michael. So hello everyone, and this is the second part of this tutorial on the computing memory. So in the first part of the tutorial, Professor Michael Lima and Professor Uramutlu have talked about the computing memory from the device aspects and also the architectures aspects. So in this talk, we are going to talk about the circuit level aspects, try to bridge the device technologies to the computer architectures. And in particularly, we are here to talk about the prototypes that are implemented into the silicon. And we talk about the technologies from SRAM to RRAM. All right, so this is the outline of my talk. So first, I will briefly go over the background of the computing memory. And then we will talk about some prototypes in the SRAM and also RRAM. And then I will talk about the overall design challenges in the computing memory. And then I will briefly talk about how to extend a circuit level macro towards a system. All right, so this is the motivation for the hardware accelerators for artificial intelligence or machine learning. And as you are aware that the GPU still dominates the training in the cloud. And we see that FPGA is becoming a good choice for the inference, especially if you want to do faster prototyping, because the network models are developed in a very fast rate. And also we see that the digital ASIC solutions, for example, the Google's TPU is ramping up in both cloud as well as the edge. So if you look at those computing platforms here, we have a metric for the energy efficiency in the tera operations per second per watt. Essentially is the throughput divided by the power. So if you look at the conventional computing platforms like GPU or FPGA, the best they can achieve is about 0.1 teraops per watt. But the GPU can support very high accurate computation because it's floating point precision. And if you look at the digital ASIC solutions such as TPU, it can improve the energy efficiency by at least one order of magnitude to about like 1 to 10 teraops per watt. And typically they employ the fixed point computation, for example, 8-bit computation. And if we want to further boost the energy efficiency, then we may want to move from digital to analog domain. And here we believe that the analog CMOS approach, especially this computing memory architecture with SRAM or emerging non-volatile memories, can further increase the energy efficiency to like 10 to 100 teraops per watt. And typically for those analog computation, we have to employ low precision computation because of the vibration noise and those issues. So this may bring the question whether we can achieve the same accuracy as the digital computation. So I will try to address this issue in the later part of the talk as well. So here, to quickly summarize, to further improve the energy efficiency, TOPS per watt, we believe the analog computing memory, possibly with an emerging non-volatile memory, is a promising approach. And we believe that this is suitable for the edge inference, where the power is very constrained. And also, we may enable some adaptive transfer learning with continuous, possibly unlabeled dataset as the edge. And let's look at the basics of the computing memory approach compared to the, let's say, conventional digital ASIC-based accelerators such as TPU. So on the left-hand side, we have the conventional accelerators architecture. And here, typically, it consists of many PEs, processing elements, which are built upon the digital multipliers and adders. And then all the weights and the activations of the neural network model are stored in the global buffer, for example, the shared SRAM cache. When the computation happens, those data will be fetched into the PEs to do the actual computation, and then the output, for example, the activations, will be sent back to the shared buffer. On the other side, on the other hand, the computing memory approach will use a different data flow where the weights are stationary in the memory arrays. So here we see many of this CIM macro. And within the macro, then here we will load in the input vector as voltage vectors to enable multiple rows. And then we will get the output vector in parallel from the columns. So this is essentially the analog compute within the memory array. And you can see that in this computing memory approach, the weights are stationary. We only move the input and output vectors. Therefore, we can reduce the data movement. And also, we can enable this parallel access and eliminate the digital MAC units. So those are the potential benefits of this computing memory approach. So let's take a closer look at the memory array if we want to support this kind of mixed signal compute. Although within the memory array is analog compute, but still the interface is digital in most cases. So we will load in the vector in the digital format, and then we may enable multiple rows, either cycle by cycle, or sometimes we can use DAC, the digital to analog converter, to activate and let's say to enable the rows with different voltage levels. And then the voltage will be multiplied by the conductance of the memory. And then we will result in a current. And the current will sum up along the column. So essentially we use the bit line to do the current summation. And then this analog current may be converted to the digital bits through the ADC, analog to digital converter. And after that, if we consider the precision of the weights, we may have to do the shift and add. For example, multiple columns represent different significance of the weights. Then we need to do the shift and add to compute the output. In terms of the memory technologies that can support this kind of computing memory, and I think Ono already talked about the DRAM-based mixed signal computation. And in this talk, I will focus mostly on the SRAM and also the emerging non-volatile memory, in particular, RRAM technology. So in the SRAM and cell, typically we can use 6-transistor SRAM, and also we can modify the SRAM bit cell to enhance the functionality as we see later. And in the RRAM or emerging non-volatile memory-based approach, typically we can have the 1T1R as a bit cell. So one transistor control one non-volatile memory element, for example, here a variable resistor. And let's look at the recent prototypes with the SRAM first. So why SRAM for the computing memory? Because SRAM is mature silicon CMOS technology. And it has been scaled to the 5 nanometer today, and also possibly for the 3 nanometer very soon. And very large capacity has been demonstrated for cache. For example, at 7 nanometer or 5 nanometer, 256 megabits has been demonstrated with SRAM technology. So SRAM actually extends if you think about the advanced technology node. And there are many variants listed for the SRAM bit cell. And we can use that for the computing memory. So here we show different bit cell structure. And the first one is a conventional 6-transistor SRAM. And here let's look at how we use this SRAM cell to do the computation. So for example, let's assume the weights we stored here, like 1 and 0. And then the activation will enable the VLAN. And then we will have the current flowing from the right-hand side passgate transistor in this case, because the bit line will be pre-charged to VDD, and then here there will be discharge current to the right-hand side passgate transistor. While the left-hand side will have very minimal current discharge if the bit line bar is also pre-charged. So then we can get the large current from the bit line and the small current from the bit line bar. And this is just for one bit cell. But if you imagine we can have a column of such cells, then we will accumulate the current from bit line or bit line bar. And then depending on the data pattern and the input vectors, so the number of cells activated along the bit line or along the bit line bar will be different. And we can use that to do the computation. And the second bit cell here is a split 6T cell. So here the modification is to add additional word line bar to separately control those two passgates. So you can have individual control of those two passgates. By doing so, we can do so-called the XNOR operation. Because here, for example, if the word line bar is 1 and word line is 0, so in this case, then the current discharge will be from the bit line only. So in this case, the bit line bar will be completely off here. So you can have larger sense margin compared to the conventional 6T design. And also, we may increase the number of transistors to the bit cell, for example, by adding 2 more transistors to have this so-called redecoupled bit cell structure. So the problem with the 6T SRAM cell for the computation is that when we enable multiple rows, then there may be the disturb issue to the SRAM cell, as the current is going to directly flowing through the storage node. In order to decouple this kind of read and write paths, so we add 2 more transistors here as a, let's say, a pull-down network. One is controlled by the read word line, other one is controlled by the storage node. So in this case, if the read word line is 1, but the wait here is 0, so still there's no current flow from the bit line, read bit line. But if the, let's say, the data pattern is reversed, then here this transistor will be turned on. So then we will have the current discharge from the read bit line. So then we can still do the computation here. And we will not affect the data pattern stored in the 6T cell because the read is performed through those 2 additional transistors. And also sometimes we can do the transpose readout with this kind of AT cell because sometimes for the training purpose, we need to bidirectionally access the data from both the row side and the column side. And then we can have this kind of bidirectional read. And for example, this is a column read, and then if you do the transpose operation, then you can enable the column and then read from the row side. So this is particularly good for the training. All right, so in the next, we have a survey of the recent SRAM-based computing memory design implemented in silicon. So those are gathered from the top conferences like ISCC and the VOSI symposium. And here you see that they are implemented from the old technology and to the latest technology. And the cell structure are described in the previous slide, from the conventional 6T to the split 6T to the AT to the transposable cell. And the bit cell size range from those values. And the array size typically like 64 or 128 up to like 512. And here is the capacity. And this for different precisions. The earlier designs only support one single bit operations, but the latest design support like multi-bit computation. And here is the energy efficiency number. And here I want to clarify one ambiguity in the literature about the TOPS per watt. So TOPS per watt should be referred to a particular precision, and that's the computation support. And different designs may support different precision, and then they need to be normalized to the same criteria. So here we normalize all the computation to 1-bit MAC operation. So that means by nature, 6P, let's say 8-bit by 8-bit MAC will be 64 times better in the energy efficiency than the 1-bit by 1-bit MAC operation. So if we convert that, then you can see those amazing numbers for those designs, like 5,000 teraops per watt. So this is for the latest technology, 7nm SRAM-based design. And this is the accuracy for different kind of applications. And this is the continued slide. I will skip the details, and the slides will be available after the tutorial. All right, so we will pick a few designs and talk about the essence of the designs. So this is one of the representative work published by the National Tsinghua University, and my group also participated in this project. So this design was based on the split 60 SRAM cell using the compact rule by the foundry. And here is the demonstration. And this one only supports the binary precision. So it supports those so-called XNOR nets and the binary neural network. So let's look at some of the key features of this design. And here we have this split 60 cell structure. So where the VRLAM and the VRLAM bar can independently control the cascades. And so we can implement the XNOR computation. And also we employ the bit clamp transistors to avoid the bitline to drop to a very low value. Because this is a 60 cell, so if the bitline drop to very low value, then the rate disturb will happen. So we want to avoid that. So we employ this kind of bitline clamp transistors to avoid that. And also we employ common mode insensitive voltage sense amplifiers to try to distinguish the current between the bitline and bitline bar, because here we have to get rid of the offset. So we employ some of the advanced techniques to cancel the offset of the sense amp. So this is one of the earlier design. And in the next year, in 2019, we also improved the design. And then we employ a different bit cell for the twin 80 bit cell. So now we can support multi-bit computation. And so here the maximum precision we can support is 4-bit input, 5-bit weight, and 7-bit output. So here in this design, we also employ the tooth complement code to implement the positive weight and negative weight. And here are some key features of this twin 80 design. So here is a twin of the 80 cell. That means we have two 80 cells. Because we can implement the most significant bit and the least significant bit. So here those two 80 cells will be combined to the grid bitline here by sizing up the transistor of the most significant 80 cells. So here the cascade transistor size, W over L, will be twice of those cascade transistors of the least significant 80 cells. So by sizing up the transistor size, we can directly combine the current in the anode domain through the read bitline. And this is the layout of the twin 80 cell. So I will skip the details of the other key features here. And recently, like the foundries, TSMC also tap in this field. And they can use, of course, the latest technology, like 7nm, and use the similar design as what we showed in the earlier slide, the 80 rate decouple cells. And this is available in the foundry layout rule. And here in this case, 4-bit weight, 4-bit input can be realized. And they use the charge sharing with the capacitors to do the analog shift and add to realize 4-bit flash ADC. So I will talk about the key features here. So the idea is simple. So because SRAM is binary in the nature, so if we want to implement 4-bit weight, then we have to use 4 columns to represent the significance. And we can directly do the analog shift add before the ADC. And here the idea is to use the capacitor array with different capacitance to do the charge sharing. I think here are 2 steps in the computation. First one is sampling, second one is to do the analog shift add. In the sampling mode, because we have to compensate for the different RC delay, so I think they have a compensation caps. So you can get similar latency from multiple columns. And then in the second stage, then they will do the shift and add by redistributing the charges through different capacitors with different capacitance. So you can represent different significance. And after that, then the flash ADC can detect the voltage at the end of the column. Then it can be digitized to the digital output. So this is the latest design with 7nm SRAM, and this one is the best one, achieving this 5,000 teraops per watt if you use the definition of 1-bit by 1-bit MAC. All right, so this is a quick summary of the SRAM-based design. So SRAM is a mature candidate for computing memory because it has a state-of-the-art availability at 5nm, for example, by TSMC. And the impressive energy efficiency has been shown in the prototypes in silicon. And leakage will be the main disadvantage for large capacity SRAM array, because as you know, SRAM is always leaking, even in the standby mode. 6T SRAM cell is the most compact cell, but it is not readily coupled. So rate disturb is a problem when multiple rows are activated. Lowering the VLAN voltage may help, but the maximum number of VLANs that can be turned on simultaneously will be limited, for example, 64. 80 SRAM cell can decouple the read and write path, offer more flexibility in the design, but of course, come with the area overhead. And typically, Foundry will offer like 60 and S80 SRAM compact design rule. If you want to further change the bit cell beyond the 60 or 80, sometimes people propose like 10T or even 12T, then you may have to use a logic design rule that is handcrafted, which will have much lower density. Like, for example, like 2 to 4 times lower density than the Foundry compact design rule. In the older technology, for example, 65nm, there are more flexibilities you can modify the bit cell. But in the advanced technology node, like 28nm or beyond, so Foundry typically will not allow you to change anything. So then you have to follow the Foundry's design rule and to design the SRAM-based prototypes. All right, let's move on to the next topic, the RRAM-based prototypes. So why RRAM? And Michael has already introduced the basics of the RRAM devices. So basically, it's a 2-terminal resistor where you can change the resistance by applying positive or negative voltages. So compared to the SRAM, RRAM offers much smaller cell size, possibly multi-bit per cell at the same technology node. So I have to emphasize at the same technology node. This is because SRAM has been scaled down to 5nm, but RRAM is still at 22 or 28nm. So you cannot compare different technology at different technology nodes. And RRAM can potentially host most of the weights on chip if we can, for example, have larger than 100 megabytes embedded RRAM. Then you can reduce or even eliminate off-chip DRAM memory access, which is a bottleneck of the system performance. And also RRAM is non-volatile. That means you can power off the chip in the standby mode without losing the data. So this is very beneficial for the dynamic power gating for the edge devices where the standby may be frequent. You cannot do this with SRAM because SRAM you have to maintain the data by powering on the VDD. Of course, you can reduce the VDD, but still you need to maintain that. So RRAM is potentially backend of RAM compatible for 3D stacking, so you can even consider multiple layers of RRAM eventually. And RRAM is becoming technology mature with the foundry availabilities. For example, TSMC is offering 40 nanometer RRAM commercial process. And also Intel recently reported 52 nanometer RRAM in ISCC. And also there are many other RRAM vendors, for example, Wenbang, Sony, Panasonic, they have their RRAM processes available as well. So due to this reason, in the recent years, there are many RRAM-based computing memory prototypes in silicon as well. So here, again, I gathered the information from the major conferences or top journals. And as you see that the technology node of RRAM is typically lagging behind the SRAM. So the latest one is 22 nanometer RRAM, and this is, I think, from TSMC as well. And here the capacity of the RRAM can be much larger than the SRAM. And also the array size can be larger than the SRAM in most cases. And here we can also support different precisions using different kinds of ADC. And here the number of rows that can be turned on can vary. So some designs can only turn on 9 rows, some designs can turn on 64 rows. And here the energy efficiency is also normalized to 1 bit per meg, 1 bit meg. As you can see here, that energy efficiency actually is worse than the SRAM-based design for most of the RRAM designs here. And here, as are more RRAM-based designs, I will skip the details. So I will just talk about a few designs that are representative. The first one is from National Tsinghua University in Taiwan. So this one is using the 55 nanometer CMOS logic process, and the RRAM is the logic process compatible. I think this RRAM is from TSMC. And in this design, it uses 1T1R, and then it is 1 bit per cell. That means it's binary. And we can see some of the features of this design. So I think one of the features in this design is a downscaling weighted current translator. So this is because in this technology, I believe the RRAM current is very large if you turn on multiple rows. So at the end of the column, so here's the current mirror, try to scale down the current of the column before you send the current to the ADC. So there's current mirror to scale down the current here. And this is an improved version from the same group, but use a more advanced 22 nanometer CMOS logic process, still from the TSMC 1T1R based RRAM. Still, this RRAM technology is 1 bit per cell. And in this design, it uses tooth complement weight mapping to support the positive weight and negative weight. And here, a reasonable inference accuracy is demonstrated for CIFAR10 dataset based on ResNet20 network model. And here are the key features of this design. And I think the key features here is the tooth complement value combiner. I will skip the details. If you are interested, I encourage you to read that SCC paper. And next, I will talk about some of our work with a collaboration from Arizona State University, Professor Jason Seal's group. So here we designed a prototype with Wenbang technology at 90 nanometer. And here we first try to implement the XNOR computation. So we use 2 1T1R cells. The reason is that we need to also implement the elective input. So we need word down and word down bar, the complementary input to do that. And then here we employ 3-bit flash ADC. And here we also achieve reasonable accuracy for the MNIST. But you see that for CIFAR10 dataset, there's a degradation of the accuracy because here we only have binary and neural network. One noticeable advantage of this design is that we turn on all the rows simultaneously. So the throughput is much improved compared with the previous work by the ISCC 19. And here we can improve the throughput by 20 times better. And if you consider the EDP, that is the throughput multiplied by the energy efficiency, or essentially is the energy delay product, then we can be 10 times better. So here are the key features of the design. As I said, we use two 1T1R cells to represent the positive weight and negative weight, and also the positive input and negative input. So we can do this X-NOR computation. And at the end of the column, then we have a poor PMOS, and then this node voltage is the voltage that representing the partial sum. And this voltage will be sensed by a flash ADC based on 7 voltage mode sense amplifiers. And in our recent work, we try to push this technology because in this one-bond technology, the on-off ratio of the RRAM is very large, can be more than like 150. So we can insert multiple states between the very on state and very off state. So we can achieve the multi-level per cell. So in this implementation, we use 2 bits per cell. So here is the programming results of the test array. So we have 4 states programmed to the RRAM. And then you can see that we try to tighten the distribution aggressively. So here the distribution is very tight for most of the RRAM. Only the tail bits will have large deviation. So with this approach, we can further increase the density because now one memory cell can store 2 bits. And recently we have done some experiments on this test array, and we found that 3 bits is also possible. So here are some key features of this design. To implement the, let's say, the 4 levels weight, then we need to program those cells with different conductance states, and we use 4 states to represent that. So I will skip the details. This work was recently accepted by the solid state circuit letters. All right, so let's summarize the RRAM-based design. So typically people will use 1T1R or 2T2R, and then the cell area typically range from 30F squared to 60F squared. So this is about 2.5 times to 5 times higher density than the SRAM as a same technology node for binary states. If the RRAM can store multiple states, then the density advantage will be even larger as a same technology node. So this is what I described here. As for the multi-level states, there are some optimizations we need to do. For example, we need to care about the relaxation after the programming, drift all the resistance, retention at a higher temperature. Make sure that the weight you program into the RRAM will be stable over time. And also the RRAM-based design will face challenges in the higher programming voltage and also the low on-state resistance. I will talk about that more in the next few slides. And typically, iterative rate verify is needed to accurately program the RRAM states. And this is okay for the inference-only design because you only need to do it one time. This will be difficult for in-situ training where you need to frequently change the states. RRAM scaling next behind SRAM. State of the RRAM is available at 22 nanometer node, for example, from TSMC and Intel. But this may be a sweet spot for low-cost edge platforms. So if you care about the cost, then maybe 22 nanometer or 28 nanometer is let's say a sweet spot from the cost perspective. All right, next I will try to summarize the design challenges or lessons from those prototypes. So the first challenge we learned is the ADC area and power bottleneck. So this is the power breakdown measured from our prototype chip. And you can see that the RRAM array with the sense amplifier or the ADC take about 80% of the total power. So ADC definitely is power hungry. And the requirement for the ADC for computing memory actually is very unique. It does not need to require super high resolution. Typically like 3-bit to 6-bit ADC, good enough for most applications. And the data rate is not very high either. But there are stringent requirements on the area of the ADC. This is because the memory array is typically very tight pitch. So here, for example, for the RRAM array, you can think you only have one transistor, one resistor between two corners. So the corner pitch is very small, but the ADC size can be very large. Then the challenge here is to share the ADCs among the corners. For example, 8 corners have to share one ADC. That will reduce the throughput because you need to do time multiplexing. You need 8 cycles to read out all the 8 corners. So this is a very stringent requirement on the area. So here we did some comparison between SAR ADC versus Flash ADC. As you know, Flash ADC is based on multiple comparators. For example, the simple voltage mode sense amplifiers, but we can have different references. And SAR ADC is just based on one comparator, but it can dynamically change the reference through the SAR logic by a binary tree kind of search. So if you compare the area, latency, and power and energy of SAR ADC and Flash ADC, the typical conclusion will be SAR ADC is preferred for the higher precision. For example, larger than 4 bits. Below 4 bits, like 3 bits, Flash ADC actually is a good choice. The second challenge we see is the variations with the analog compute. So this is inherent with the analog compute because you have to deal with variations, deal with the noise. So due to those variations, the inference accuracy could be degraded from the software baseline. So that's why you see the degradation of the accuracy, for example, from 90% for the CEPA10 to like 80-something%. The primary variation sources include the cell-to-cell unstable resistance variation from the memory cell and also the ADC offset. But we would argue that the cell-to-cell unstable variation could be minimized by the iterative write and verify technique. For example, this is experimental data from our test array. So here we try to program the RRAM resistance to 8 kilo, and the first programming will have the wider distribution, but we can reprogram and with multiple iterations, then we can gradually tighten the distribution. ADC offset is more critical because we cannot tune it by this kind of programming. And so we have to use advanced offset cancellation, but that will further increase the area of the ADC, which is already a very stringent requirement. So here we started the impact of ADC offset. And here we run the Monte Carlo simulations. So you can see the actual ADC output may vary around the ideal ADC output. So it's not a straight line here. So with this kind of variations, then the inference accuracy will degrade. And one of the techniques to recover this kind of degradation is to do the retraining of your network model. That means you have to adapt the network to each individual chip instance to compensate for this kind of variation. So after each chip is manufactured, you can possibly run the inference and then do some retraining. So you fine tune the weights. So here, if you do that, you can recover this kind of accuracy loss. So here are some experiments running on the CEPA10 data set, try to recover the accuracy loss by the fine tune of the weights. The challenge 3 is the low resistance of the RRAM and high weight voltage. So if the unstable resistance is low, so the calling current will be large. So we have to size up the max at the end of the calling. So this takes a lot of area. And also the high voltage of the RRAM. For example, if you need like 2 or 3 volts to program, then this is higher than the logic supply voltage, like 0.9 volts. Then you need the level shifter to convert the voltage domains, and this will take a lot of space, as shown in our layout. So those are the challenges from the device properties perspective. So here, the desired device engineering targets will be on state larger than 100 kilo ohm, and the write voltage compatible with the logic, for example, 1 volt. So this still needs the device engineering efforts. So lastly, I will quickly talk about how to extend the circuit macro towards the system. So right now we have shown those prototypes, but this prototype is just a single memory array or maybe a limited number of the memory arrays. It's far away from a whole system to implement a full, complete neural network model. So typically, right now, this one macro can only implement maybe one layer of the model. So how to do that? Then we have to consider the system, consider the data flow and weight mapping strategy. So here we just have one example to if we want to support the on-chip training. So if we want to do on-chip training, so we would think that SRAM is a better choice because of the fast read and also the very large endurance. So here for the transpose for array, we can have this kind of design. And I'll give the details. The design was published in this year's ISCC. So we can have the forward computation. And also then we can have the transpose computation for the backward propagation. So this is the chip macro we taped out, and it is just for one array. But for the neural network model, we need many of these kind of arrays. Right now, we don't have resources to do the full system design and tape out. So what we can do is to use the parameters from this one macro and then build a system and considering the data flow and the peripherals logic. For example, you may need the accumulators and adder trees, combine the partial sums from multiple arrays. So to enable this kind of system level study, our group published the neural sim framework to do this kind of design space exploration. I will skip the details, but this model is available publicly on the GitHub. So there are two versions. One is for inference, one is for training. So we can take the parameters from one macro and then report the overall system performance, considering mapping a whole network onto multiple arrays. So with this kind of approach, we can benchmark the performance of different neural networks. And here I just want to give an advertisement for my student's talk, who is going to give the paper presentation on this Wednesday on the on-chip training using this kind of transposable SRAM macros. So I will skip the details. So if you are interested, please watch the video on Wednesday. Okay, so finally I will summarize. And as you see that the computing memory saves the intermediate data movement, thus improves the energy efficiency and throughput. And computing in SRAM at advanced node, for example, 5 nanometers, still performs the best. Today's RRAM can be tuned into multi-level space, possibly by iterative programming. And we believe that offline inference still the most suitable applications with advantage over SRAM in terms of the leakage. And the slight inference accuracy degradation is caused by the variation at ADC offset. So this may bring the overhead of the testing and the retraining. RRAM-based design still faces the challenges as we see the high voltage and the low on-state resistance. And our group provided this framework in a neural sim to benchmark different technologies, and that is open source to the community. And the emerging non-volatile memories, for example, the ferroelectric transistors, SOT-MRAM, that Michael introduced in the other talk, could be the possible future research area because those devices may offer increased on-state resistance. So with this, I'd like to thank my collaborator, Professor Menghan Chang, on the SRAM-based design, Professor Jason Steele on the RRAM-based design, and of course, the sponsors of this research. I'm happy to take some questions.
Thanks, Shimang. If you wanted to ask a question, I think we have time for maybe 2 quick questions. I see somebody already has raised their hand. It looks like Payman. Let me unmute you if you want to ask your question or try.